We're now going to go ahead and take a look at the implementation of the AtomicLong StampedLock class. And this particular class implements a subset of the abstract long interface we talked about before. And this time it's going to use StampedLock in order to illustrate StampedLock's optimistic read locks, show its pessimistic write locks, as well as its conditional write lock. So first of all, here's the field that will be manipulated atomically by the various methods. This is just a long that's called M value. Note that this long is not volatile, so it has to be protected by some type of lock, be it an optimistic read lock or a read lock or a write lock or whatever. We then go ahead and create ourselves a stamped lock. And this stamped lock is also a field, and we'll use this to give the appropriate serialized access to M value depending on what kind of operation we're doing, be it a get or an increment and get or a decrement and get or a get and decrement and so on. The constructor for AtomicLong StampedLock simply takes the initial value and assigns it to the M value field. So far, so good. Really hasn't been too complicated. Let's start taking a look at some of the interesting features we have here for StampedLock. The first one we're going to demonstrate in the context of the get method. So if you recall, the get method returns the current value, except this particular implementation is going to return that current value using a so-called optimistic read lock. And we'll see what that means in just a moment. So the first thing we do is we come in here and we define a local variable, and this variable is used to keep track of the value. And this particular value, as we'll see, is going to be updated using an optimistic read. What does that mean? Well, first thing we're going to do is we're going to go to StampedLock and say, please get me an optimistic read lock. Now, an optimistic read lock isn't really a lock at all. It's essentially kind of a timestamp that keeps track of the fact that someone is trying to do an optimistic read. And with that, quote, stamp held, using the word stamp held very loosely, we then try to assign the value of M value to the value of the local variable. Now, keep in mind that this local variable is thread safe. There's no other thread that will be manipulating it, but there could be a thread that's manipulating M value. In particular, there could be a thread that's trying to write to M value at this point. And in order to do that, of course, we'd have to grab the write lock. So what we're going to do now is we're going to go ahead and validate that stamp. And when we call validate, it will return true if nothing changed M value, or more specifically, if no other thread acquired that stamp lock for writing between the point where we got this optimistic read timestamp and when validate was called on it. If nothing happened in there, if there was no write operation, then all is well. Value is a consistent value, and we just return the value. And you'll note in that case, we never really held the lock. All that we do is validate does a little magic to do some cache flushing so that the value will be propagated appropriately throughout the system. But otherwise, it doesn't actually lock anything. However, if there was a write that occurred here, if a write lock was acquired in this very small window, we're going to get a false value back, in which case we turn around and we use the read lock call, which actually blocks until we get a read lock. Once we have the read lock, of course, then we can turn around here and return the value with the read lock held. That's perfectly consistent. No issues with memory inconsistencies here or caching. And then on the way out, we unlock the lock, which we know was a read lock at that point. And we always do that in the context of a finally block. Just a good habit to get into. Now, obviously, this call is not going to throw an exception, so it's a little overkill to do this, but you'll thank me some point when you change this to something else that might throw an exception, in which case doing the unlock in the finally block will be good. Let's take a look at a couple of other methods. This is increment and get, and you can see it uses a so-called pessimistic write lock. And it's pessimistic because it always blocks. Either it gets the lock right away or it's going to have to block to get the lock. And therefore, even if there's no other contention, it's still going to have to go to the trouble of getting a write lock. Now, if there's not much contention, that won't take very long, but it's longer than not doing a lock. So in this case, assuming we've gotten the write lock, then we can go ahead and increment and return the value with the write lock held, and then we unlock the write lock. You'll notice when we acquire a write lock directly, it's usually a good idea to explicitly unlock it with the unlock write method. You could get away with just using unlock, but that's a little bit more overhead, and this is more clear what's really going on. We can do the same thing for decrement and get. We get a write lock, which could block. We then decrement the value and return the decremented value, which has now been decremented as well. Then we unlock the write lock. Now let's take a look at a more interesting example. This is going to use a so-called conditional write lock. It's a lot more complicated, not necessarily a win always, but on situations where it is a win, it's kind of cool. So let's take a look and see how it works. So the first thing we're going to do is we're going to come in here and we're going to block until we get a read lock. And then we're going to go ahead and set this local variable, which is going to be used to hold the value. And we'll set that to 0 just to give it some sensible default. Now, we do a try finally block so we can always make sure we unlock this properly in the finally section. And then we're going to keep looping until we get a write lock. And this is the conditional write lock part. So the way this is going to work is the first thing we're going to do is we're going to read the value of m value, which notice we have a read lock. So this is a perfectly valid read. Value is consistent at that point. And then we're going to do a little magic by trying to convert the read lock into a write lock. And if all goes well, then we've got ourselves a write lock. And we know that because we'll get back a value of a return value from try to convert write lock, which is non-zero. If that's the case, we're done. We increment the value. We set the stamp to be the write lock that we got. We break out of the loop, and then we unlock the write stamp, and we return the incremented value. However, if we're not lucky and we don't get a conversion because someone else already holds the write lock, because we started out with a read lock and we couldn't do the immediate conversion, in that case, we unlock the read lock, and then we block until we can get a write lock. So when we loop back around the second time, this conversion will always work because we have already converted it to a write lock. And now we'll do this loop one extra time. It'll work. We'll break out. We unlock the write lock and we return the value. So notice how we always unlock it as a write lock, even though we initially acquired it as a read lock. So that you can basically think of this as sort of conditional writing, or really read lock upgrading might be another way to look at it. We do the same thing for the get and decrement. Same approach. We get a read lock. We go into a loop. We read the value into a local variable. We try to do the conversion to a write lock. If we succeed, we decrement this time, and then we're done, and we unlock the lock and return the value. Otherwise, just like before, we unlock the read lock, we block till we get a write lock, and now this time when we loop back around again, we know that that's going to work. So that's basically the walkthrough of the AtomicLong stamped lock implementation, showing off a bunch of different cool features of stamped lock.